Our universe is flying apart at a speed that should be impossible. Galaxies are not simply moving away from each other. They are accelerating, racing into the void faster every moment. This discovery shattered a fundamental pillar of physics, revealing that our most trusted laws of gravity fail to explain the cosmos. By the end of this, you will understand the true nature of this cosmic defiance and what it means for the ultimate fate of everything. We will uncover the mysterious force known as dark energy and explore why empty space itself seems to be pushing the universe apart. How do you think our understanding of reality will change when we finally solve this puzzle? Edwin Hubble peered through the Great Telescope at Mount Wilson and saw a universe in motion. In the 1920s, his meticulous observations of distant galaxies revealed something astonishing. The light from these island universes was stretched, shifted toward the red end of the spectrum. This redshift was a cosmic speedometer, and it showed that nearly every galaxy was racing away from our own. The universe was not a static, unchanging backdrop of stars. It was dynamically, undeniably expanding. This discovery was a perfect match for Einstein's own theory of gravity, which described a cosmos that could not stand still. Hubble then gave us a crucial rule now known as Hubble's law. The farther away a galaxy is, the faster it appears to be receding. This painted a clear and elegant picture for astronomers. Imagine a loaf of raisin bread rising in the oven. As the dough expands, every raisin moves away from every other raisin. The farther apart two raisins are, the more dough expands between them, and the faster they seem to separate. This was our universe, a cosmic loaf steadily and predictably growing larger. For decades, this was the accepted narrative, a beautiful story of a universe born in a fiery beginning and cooling as it gracefully swelled. But this elegant model was about to be shattered. The steady expansion described by Hubble was merely the prelude to a much stranger and more dramatic chapter, one where the universe itself would begin to break its own rules. For decades, the universe seemed to obey a simple, predictable rhythm. Then, in the late 1990s, that rhythm was broken by the light of dying stars. Two rival teams of astronomers were hunting for distant cosmic explosions known as Type 1, a supernova. These stellar blasts are special because they all explode with nearly the same intrinsic brightness, making them perfect cosmic mile markers or standard candles. By carefully measuring how bright these supernovae appeared from Earth, the scientists could calculate their true distance with incredible precision. And by studying their redshift, they could determine how fast the universe was expanding in the distant past. The goal was to measure the cosmic breaks, to see how much the pull of gravity had been slowing down the expansion since the Big Bang. The results, however, were not just unexpected, they were impossible. The distant supernova were significantly fainter than they should have been. This meant they were much, much farther away. The only way this could happen was if the expansion of the universe had not been slowing down at all. Instead, it was speeding up. Something was forcing galaxies to fly apart from each other faster and faster with every passing moment. The discovery was so revolutionary, so counter to all established physics, that the teams assumed they had made a mistake. They spent months checking and rechecking their data for any possible error. They searched for interstellar dust that could be dimming the starlight. They questioned their instruments and their methods, but the data was relentless. The conclusion was inescapable. The cosmos was not just expanding, it was accelerating. This finding was so profound it earned the team leaders the Nobel Prize in Physics in 2011. In an instant, our understanding of the cosmos was turned inside out. Gravity, the force that pulls the universe together, was being overpowered by a mysterious, repulsive force pushing it apart. The universe had thrown a paradox at the very foundation of physics, and we were only just beginning to understand the questions. This paradox strikes at the very core of our intuition. We have all thrown a ball into the air and watched it arc gracefully back to the ground. We know, without even thinking, that gravity is a force of attraction. It pulls things together. It keeps our feet on the ground and our planet in orbit around the sun. For over 3 centuries, since Isaac Newton formulated his laws, this has been the unchallenged narrative of gravity. It is a force that gathers, that collects, that slows things down. So when we apply this logic to the entire cosmos, the conclusion seems inevitable. The collective gravitational pull of every galaxy, every star, and every particle of matter in the universe should be acting as a cosmic brake. The expansion from the Big Bang should be steadily slowing, like a car coasting up a long, gentle hill, destined to eventually stop and then reverse into a great collapse. The discovery of acceleration is the equivalent of watching that car, instead of slowing, suddenly press the accelerator to the floor and speed away faster than ever. This is not a small adjustment to our theories. It is a direct violation of a fundamental expectation built into the very fabric of physics as we know it. How can the universe be doing the exact opposite of what every law we trust says it should? This is the magical and deeply unsettling nature of the mystery we now face. The irony of this cosmic acceleration is that its solution might have been written in the equations nearly a century ago. Albert Einstein himself stumbled upon this very possibility. As he worked on his monumental theory of general relativity, his mathematics described a universe in motion, one that could not remain still. It had to be either growing or collapsing. Yet the scientific consensus of his time, including his own belief, held that the cosmos was eternal and static. To force his brilliant equations to match this incorrect assumption, Einstein introduced a mathematical fix, a term he called the cosmological constant. Symbolized by the Greek letter lambda, this was a repulsive force, a kind of anti-gravity woven into the fabric of space itself, designed to perfectly offset the inward pull of all matter and keep the universe frozen in place. When Edwin Hubble later demonstrated that the universe was indeed expanding, Einstein saw his intervention for what it was, an unnecessary complication. He reportedly declared the cosmological constant his greatest blunder and removed it from his work. For decades, it was a footnote in the history of physics, a cautionary tale about forcing nature to conform to human expectation. But the universe, it seems, has a profound sense of humor. The discovery of accelerating expansion has brought Einstein's discarded constant back from exile. Today, it stands as the simplest and leading explanation for dark energy. That same repulsive force he invented to hold the universe still is now the very thing we invoke to explain why it is flying apart ever faster. An idea once thought to be a mistake now sits at the heart of cosmology's greatest mystery. It is a powerful reminder that the answers we seek are not always ahead of us, but sometimes waiting patiently in the past, hidden within the very rules we thought we had already mastered. For nearly a century, the fate of the cosmos seemed to hinge on a simple contest of strength. On one side was the explosive momentum of the Big Bang, an initial outward rush that set every galaxy flying apart. On the other side was the relentless, gathering pull of gravity from all the matter in the universe. This was the ultimate cosmic tug of war. The final outcome depended entirely on the total amount of matter and energy. If their collective gravity was strong enough, it would eventually overcome the initial expansion. pulling everything back together in a fiery reversal known as the Big Crunch. If the density was too low, gravity would lose its grip and the universe would continue expanding forever, its galaxies drifting apart at an ever-slowing pace. This was the elegant two-choice future laid out by our best models, but the discovery of acceleration did more than just add a third option. It revealed that this entire battle was being decided by a ghost. A mysterious component we call dark energy has entered the contest, and it is not just a minor player, it is overwhelmingly dominant. This force does not pull things together. It pushes them apart, creating a kind of negative pressure that actively stretches the fabric of spacetime. Think of the universe as a rubber sheet. All the matter, the stars and galaxies, and even the invisible dark matter, are like weights on that sheet, creating dips and valleys that pull objects together. Dark energy is like someone gripping the edges of that rubber sheet and pulling outward with incredible force, stretching it so fast that the little dips made by the weights become almost irrelevant. This is the profound imbalance we now see. The known constituents of the universe, everything we can see and measure, are no longer the primary drivers of cosmic evolution. They are merely floating along for the ride on a tide of something we do not understand. This points toward a gap in our knowledge so vast that it calls into question the very nature of reality. What could possibly be so powerful that it overrules the fundamental force of gravity on a universal scale? To truly grasp the paradox, we must look inside the mathematical engine that drives the cosmos. This engine is built upon the Friedmann equations, which are the direct offspring of Einstein's general relativity, translated to describe an entire universe in motion. These equations act as a cosmic balance sheet, meticulously relating the expansion rate of the universe, what scientists call the Hubble parameter, to the contents of the cosmos. They account for everything matter, radiation, and that mysterious cosmological constant. The behavior of each component is defined by its equation of state, a simple ratio that compares its pressure to its energy density. For all the ordinary matter and even the invisible dark matter we are made of, gravity is an attractive force. Its energy density is positive, while its pressure is effectively zero. This combination, according to the Friedmann equations, always acts as a brake, guaranteeing a decelerating expansion. The collective pull of every galaxy should be steadily slowing the cosmic rush. For the expansion to accelerate, the equations demand something bizarre, a component that does not pull but pushes. This requires a substance with a sufficiently negative pressure. Think of positive pressure like the air in a bicycle tire. It pushes outward, resisting compression. But negative pressure is more like a tension, a stretching force, like someone pulling on the fabric of spacetime itself. The observed acceleration is not just a slight nudge. It requires this mysterious component to have a specific and strange property, a pressure that is roughly equal to the negative of its energy density. This value is utterly alien. No known form of matter or radiation behaves this way. It defies every familiar substance in our universe, so the mathematics presents us with a stark and beautiful contradiction. The equations themselves tell us exactly what must be happening to cause the acceleration we see, while simultaneously telling us that nothing we know of can possibly fit that description. The answer is written clearly in the numbers, yet it points to a form of energy that should not exist. This mysterious force now has a name: dark energy. It is the label we use for our ignorance, a placeholder for whatever is causing the cosmos to fly apart faster and faster. Think of it as the prime suspect in our cosmic investigation, a shadowy entity that permeates every single cubic inch of the universe, from the vast voids between galaxies to the empty space inside the room you're sitting in right now. Its most baffling property is that it possesses a kind of repulsive gravity. According to the rules of general relativity, it is not mass or energy that dictates how gravity behaves, but the combination of energy, density, and pressure. For everything we are familiar with, from planets to people, this combination results in the attractive gravity we know, but dark energy is different. It has a powerful negative pressure, a stretching tension inherent to space itself. This negative pressure flips the script, turning gravity from an attractive force into a repulsive one on the largest scales imaginable. The numbers that emerge from our observations are staggering. Dark energy is not a minor component. It makes up about 68% of the entire energy budget of the cosmos. All the stars, galaxies, planets, and even the invisible dark matter that binds galaxies together, everything we thought was the main content of the universe, constitutes less than a third of the total. Dark energy is the dominant force, the silent majority ruler of cosmic fate. The simplest way to model this overwhelming presence is with Einstein's old cosmological constant, an energy density that is perfectly constant and unchanging, woven into the very fabric of the vacuum. Yet this simple solution raises profound questions. Is dark energy a fundamental property of empty space itself, a fixed price the universe pays for its own existence? Or is it something more dynamic, a new kind of field that slowly evolves over cosmic time, a cosmic cousin to the field that is thought to have powered the Big Bang's initial inflation? The most unsettling possibility is that dark energy is not a substance at all, but a glaring sign that our theory of gravity, Einstein's magnificent general relativity, is incomplete and begins to fail when applied to the entire universe. This central quest to identify dark energy is no longer a side project in astronomy. It is the front line in our struggle to resolve the expansion paradox, a search that is actively pushing the boundaries of fundamental physics and forcing us to question the very nature of reality. But this simple picture of dark energy as a property of space immediately runs into one of the greatest embarrassments in all of theoretical physics. The problem begins when we ask what empty space is really made of. According to quantum mechanics, the vacuum is not a serene, silent void. Instead, it is a chaotic sea of activity, a frothing foam where so-called virtual particles and antiparticles spontaneously blink into and out of existence in an endless, frantic dance. Every single point in space, even the emptiness inside an atom, possesses this seething quantum energy. This should contribute to the energy density of the vacuum, a contribution that should act exactly like Einstein's cosmological constant. The trouble starts when physicists try to calculate just how much energy this quantum frenzy should contain. The answer they get from quantum field theory is not just a little bit wrong. It is catastrophically, unimaginably incorrect. The theoretical prediction for the vacuum's energy density is a number so enormous it defies comprehension. It is over 120 orders of magnitude stronger than the dark energy density we actually observe. To put that number into perspective, it is the difference between the energy contained in a single proton and the energy contained in the entire observable universe. This staggering mismatch is known as the cosmological constant problem, and it represents the single largest discrepancy between a theoretical prediction and an experimental measurement in the entire history of science. If the vacuum energy were truly as powerful as quantum mechanics suggests it should be, the repulsive force would have been so immense that galaxies, stars, and even atoms could never have formed. The universe would have been ripped apart in the first instant after the Big Bang, leaving behind a featureless, accelerating void. The fact that we exist at all, that we see a cosmos filled with structure, tells us that the actual value of dark energy is not just a little small. It is fine-tuned to an almost miraculous degree, a number so close to zero, yet not quite zero, that it seems to whisper of a deeper, hidden principle governing the cosmos. We are left with a haunting question. Why is the energy of the vacuum so incredibly feeble, a ghost of its predicted self? Is there some sublime cancellation mechanism, a perfect but unknown symmetry that almost entirely erases the quantum frenzy, leaving behind only the faintest echo we call dark energy? Or does this vacuum catastrophe point to a fundamental flaw in our understanding, a sign that our theories of the very large and the very small are refusing to speak the same language? This is not a minor puzzle. It is a chasm at the heart of physics, and crossing it may require nothing less than a revolution. The evidence for this cosmic speed-up is not built on a single, fragile observation. It stands on multiple, unshakable pillars, each one independently pointing to the same startling conclusion. While the light from distant supernova provided the initial shock, it is the echo of the Big Bang itself that offers some of the most compelling confirmation. This is the cosmic microwave background, a faint glow of radiation that fills every corner of the sky. It is the cooled remnant of the universe's fiery birth, a fossilized snapshot from a time when the cosmos was just a hot, dense plasma. Satellites like Planck have mapped this afterglow with exquisite precision, revealing tiny variations in its temperature, patterns imprinted on the infant universe. These patterns act as a cosmic ruler, revealing the fundamental geometry of space-time. The measurements show our universe is geometrically flat, a finding that places a strict demand on its total energy content. When we add up all the ordinary matter and the invisible dark matter we can detect through gravity, the sum falls drastically short. Something else, a dominant component with repulsive gravity, must make up the overwhelming majority of the cosmos to achieve this flatness. That something is dark energy. Further proof comes from mapping the vast cosmic web. Enormous surveys chart the positions of millions of galaxies, tracing the large-scale structure of the universe. The patterns of clusters and voids we see today are the grown-up version of the tiny seeds seen in the cosmic microwave background. But the way these structures have evolved over billions of years also tells a story. The observed distribution and growth of galaxies only makes sense if a repulsive force has been actively working against gravity's pull, suppressing the formation of even larger structures. This multi-pronged investigation, using the death of stars, the birth of the universe, and the architecture of the cosmic web, all converges on the same inescapable truth. The acceleration is not a measurement error or a fleeting anomaly. It is a robust, fundamental feature of our reality, a paradox confirmed from every angle we can observe. This acceleration rewrites the final chapter of our universe, the cosmic tug of war we once envisioned, ending in either a fiery big crunch or a slow, cold fade, has been fundamentally overturned. The outcome now rests entirely on the unknown character of dark energy, and the possibilities are both profound and unsettling. The most conservative forecast, based on the idea of a simple cosmological constant, leads to what scientists call a heat death. In this future, the acceleration continues at a steady, unrelenting pace. Billions of years from now, the expansion of space itself will have carried all other galaxies so far away that they vanish from our observable horizon. The universe will become a truly lonely place. Star formation will cease as all the raw material for new suns is dispersed into an ever-growing void. One by one, the existing stars will burn out, leaving behind cold, dead remnants like black holes and neutron stars. even these will slowly evaporate over incomprehensible timescales. The cosmos will approach a state of absolute zero temperature, a dark, dilute, and silent equilibrium where no energy can be transferred and no new story can ever be told. This is a quiet but permanent end, yet this may not be our ultimate fate. What if dark energy is not constant? What if this repulsive force grows stronger over time? This possibility opens the door to a far more dramatic and violent finale known as the Big Rip. In this scenario, the acceleration does not just continue, it intensifies exponentially. The repulsive gravity of dark energy would eventually overcome every force that holds structures together. First, the cosmic glue of gravity that binds galaxies into clusters would fail, sending each galaxy flying off on its own. Then, the gravitational pull holding individual galaxies together would be shattered. Our own Milky Way would be torn asunder, its stars scattered into the deepening void. As the acceleration grows still more ferocious, it would target solar systems, ripping planets from their stars. In the final, harrowing moments, the force would become so powerful that it would overwhelm the very forces that bind matter itself. The same electromagnetic force that holds your body together and the strong nuclear force that binds atomic nuclei would be rendered useless. Planets, objects, and even atoms and subatomic particles would be violently shredded, torn apart by the stretching of spacetime itself. The universe would end not with a whimper but with a catastrophic tear in the fabric of reality. The quest to understand dark energy is therefore a journey to answer the most fundamental question of all. Will our universe fade into a silent, eternal night, or will it end in a moment of ultimate disintegration? The destiny of every galaxy, every star, every world, and every atom depends on the answer. Perhaps the entire problem lies not in what is missing from the universe, but in the very lens through which we view it. What if our foundational theory of gravity, Einstein's masterpiece of general relativity, is itself an approximation that begins to fail when stretched across the vast emptiness between galaxy clusters? This radical line of thought challenges us to rewrite the laws of physics rather than fill the cosmos with invisible entities. It has given rise to theories of modified gravity, the most prominent being modified Newtonian dynamics, or MN. The core idea is deceptively simple. Instead of inventing dark matter to explain why galaxies rotate faster than they should, MN proposes a subtle change to how gravity behaves at extremely low accelerations, the kind found in the outer reaches of galaxies. It suggests that Newton's and Einstein's laws, which work perfectly within our solar system, are not the final word. In the faint gravitational fields far from a galaxy's bright center, the force of gravity may strengthen slightly, providing the extra pull needed to hold fast-spinning stars in place without any need for a dark matter halo. And when extended to the cosmic scale, some relativistic versions of this idea, with names like tensor vector scalar gravity, attempt to also account for the universe's accelerating expansion, all without a single drop of dark energy. The appeal is powerful. It offers a universe built only from the things we can see and touch, governed by a single, albeit revised, set of rules. Yet this elegant solution faces a formidable wall of evidence. While man can beautifully explain the rotation of many individual galaxies, it stumbles when confronted with the grandest cosmic blueprint of all, the cosmic microwave background. The precise patterns in this ancient light are a perfect match for a universe that contains a substantial amount of dark matter, a cosmic ingredient that modified gravity theories struggle to incorporate. The observed behavior of colliding galaxy clusters, where gravitational effects appear separated from the visible matter, also poses a severe challenge. This leaves cosmology at a profound crossroads. a debate over the soul of physics itself. Do we preserve our cherished theory of gravity by populating the universe with mysterious, unseen components that make up 95% of everything? Or do we take the bolder path, declaring that our understanding of gravity itself is flawed, and begin the arduous task of rewriting the rules of the cosmos from the ground up? The choice could not be more fundamental. It is a conflict between inventing new contents for the universe and inventing a new universe for the contents we already know. This apparent balance between matter and dark energy introduces yet another puzzle, the cosmic coincidence problem. We find ourselves living in a strangely special moment. For nearly the entire history of the universe, the cosmos was ruled by other forces. In its first several 100,000 years, it was dominated by intense radiation, a blindingly hot and dense plasma. Then, for billions of years, matter took the throne, its gravitational pull governing the expansion and sculpting the galaxies. Throughout this immense span of time, dark energy, if it existed at all, was a ghost in the background, its effect trillions of times weaker than the other components. And in the far future, as space continues to stretch, dark energy will become the absolute sovereign, its repulsive force diluting matter to near irrelevance. Yet today, right now, we observe something extraordinary. The energy density of matter and the energy density of dark energy are not just similar, they are of the same order of magnitude. They are roughly comparable. We exist in a fleeting cosmic window where these two titanic forces are in a brief and delicate balance. Why this moment? Why now? The sheer improbability of this timing feels deeply suspicious. If dark energy had been slightly stronger in the early universe, its repulsive push would have prevented galaxies from ever forming, scattering the primordial gas before stars could ignite. If it had been much weaker, it would have remained irrelevant, and the universe would have continued its decelerating expansion without this current era of acceleration. In either of those far more likely scenarios, the universe would likely be sterile, devoid of the complex structures and long-lived stars necessary for life to arise. So the question becomes unavoidable. Does our existence as observers depend on this precise and seemingly fine-tuned cosmic arrangement? This is the anthropic side of the puzzle, the suggestion that we see this balance simply because we are here to see it. A universe without this coincidence might be a universe without anyone to wonder about it. For physicists, however, this reasoning feels deeply unsatisfying. A simple, unchanging cosmological constant offers no natural reason for why its energy density should just happen to match that of matter precisely at the time when intelligent life emerges. It presents this profound balance as a sheer accident, a random alignment with no deeper cause. Resolving this coincidence problem is therefore a critical test for any theory of dark energy. Perhaps the answer lies in a dynamic form of dark energy, a field that slowly evolves and naturally crosses the matter density at this point in cosmic history. Or perhaps it points to a multiverse, a vast landscape of universes with different physical constants, where we naturally find ourselves in one of the rare habitable corners. The coincidence problem reminds us that the greatest mysteries are not just about what the universe is doing, but why it is doing it at the very moment we are here to witness it. Yet in this cosmic struggle between push and pull, dark matter plays the indispensable supporting role. It is the invisible architect of the universe, the hidden framework upon which all the luminous structures we see are built. We know it is there not because we can see it, but because we can see its ghostly grip on everything else. The way stars whip around the centers of galaxies at impossible speeds, the way massive clusters of galaxies bend the light from distant objects behind them, all of it points to the presence of vast, unseen halos of matter that neither emits nor absorbs light. This dark matter provides the essential gravitational glue. In the early universe, its relentless pull gathered the primordial hydrogen gas, creating the dense seeds that would eventually ignite into the first stars and coalesce into the majestic galaxies we observe today. For billions of years, this attractive force was the dominant power, working tirelessly to slow the cosmic expansion inherited from the Big Bang. It was a losing battle, but a crucial one. Without dark matter's scaffolding, the universe would be a formless, dark sea of scattered gas, a place without galaxies, without stars, and without us. The cosmic drama hinges on the shifting balance between this ancient gathering force and the new, repulsive power of dark energy. As the universe expanded, the density of dark matter, like all matter, was steadily diluted, its gravitational influence weakening over vast volumes of space. Dark energy, however, if it truly is a property of the vacuum itself, possesses a constant energy density. Its repulsive push does not fade as space grows. Imagine a tug of war where one team, dark matter, slowly loses its strength as the rope gets longer, while the other team, dark energy, maintains its full power indefinitely. There comes a point about 5 billion years ago when the weakening pull of matter could no longer compete with the unwavering push of dark energy. That was the moment the universe shifted gears, moving from deceleration to the perplexing acceleration we measure today. To truly read the story of the cosmos, from the first glimmers of the cosmic microwave background to the grand structure of the modern cosmic web, we must account for both of these invisible titans. Their delicate interplay, the constant tension between the attraction of dark matter and the repulsion of dark energy, writes the entire history and dictates the ultimate fate of everything we see. But what if the engine of cosmic acceleration is not a simple, unchanging constant? Imagine a universe where the force pushing it apart is alive, a dynamic entity that breathes and evolves with time. This is the compelling idea behind Quintessence, a theoretical field proposed as an alternative to Einstein's static cosmological constant. The name itself, drawn from an ancient term for the fifth element, hints at its revolutionary nature, a new fundamental component of reality. Unlike a fixed lambda, quintessence is a scalar field, a kind of invisible fluid that permeates all of space. Its energy density and its repulsive pressure are not locked in place. They can change, waxing and waning as the cosmos grows older. This single shift opens a universe of possibilities. The acceleration we see today might not have been the same in the distant past, and it may not define the far future. Perhaps the universe only recently shifted into this high gear, or maybe this is just one phase in a long cosmic cycle of speeding up and slowing down. This dynamic nature offers a potential solution to the haunting coincidence problem. Some models of quintessence are designed with a kind of cosmic cunning, allowing the field's energy density to naturally follow or track the density of matter for billions of years. In this scenario, the balance we observe between the two is not a freak accident of timing, but a predictable outcome of the field's evolution, a long-held stalemate that only recently broke in favor of acceleration. While we have no direct evidence yet to confirm quintessence, its theoretical appeal is immense. It suggests that dark energy is not a fixed tax on empty space, but something far more profound, a new cosmic force with its own rules and behaviors, a fundamental player in the drama of the universe waiting for its discovery. Even as we build our most sophisticated models of dark energy, a new and troubling crack has appeared in the very foundation of modern cosmology. It is known as the Hubble Tension, a stubborn disagreement over how fast the universe is expanding right now. On one side, we have measurements anchored in our cosmic neighborhood. Astronomers use pulsating stars called Cepheids variables and brilliant supernova as their guideposts. These celestial lighthouses allow them to measure distances and calculate the Hubble constant with remarkable precision, giving us the expansion rate as we see it today. This local measurement returns a specific, robust number. Yet, when we look to the far horizon, to the afterglow of the Big Bang captured in the cosmic microwave background, we get a different story entirely. The pristine patterns in that ancient light, mapped by satellites like Planck, allow us to work backwards. Using our standard model of cosmology, we can predict what the expansion rate should be today based on the conditions of the infant universe. This early universe method yields a Hubble constant that is consistently, undeniably lower than the one we measure locally. The difference is not a small statistical fluke. It is a significant gap that has only grown more pronounced as our instruments have become more accurate. This is not a simple error. It is a direct conflict between two of the most trusted methods in all of astronomy. The local universe is telling us one speed, while the baby universe is telling us another. This Hubble tension places enormous strain on our standard model of cosmology, the lambda-CDM model that relies on dark energy and dark matter to explain everything. If our model is correct, both methods should converge on the exact same number for the Hubble constant. The fact that they do not suggests that something in our model is wrong, or at least incomplete. Perhaps dark energy is not a simple cosmological constant, but something that evolves, changing its influence over cosmic time. Maybe there is something unexpected about the early universe, a new type of particle like a strange neutrino, or a brief phase of early dark energy that altered the cosmic recipe just after the Big Bang. This tension is more than a technical disagreement. It is a potential gateway, a sign that we are on the verge of discovering physics beyond our current understanding. It tells us that the simple story of a constant dark energy might be a beautiful oversimplification, and that the true driver of cosmic acceleration is far more complex and intertwined with other profound mysteries. So we have a conflict between the local and ancient universe, a tension that threatens to crack our standard model. But what if we had a third witness, one that could measure the expansion history of the cosmos across its entire lifetime, completely independent of supernova or the cosmic microwave background? This witness exists, and it speaks through the very architecture of the cosmos, through a faint, fossilized echo of sound from the Big Bang itself. It is known as Baryon acoustic oscillations. In the first moments of the universe, it was a seething, opaque plasma, a hot soup of particles and light. In this dense fluid, gravity pulled matter inward, while the intense pressure of radiation pushed it outward. This push and pull created powerful sound waves that raced through the primordial fireball, much like ripples moving across the surface of a pond. But when the universe was about 380,000 years old, it cooled enough for atoms to form, allowing light to travel freely in an event we call recombination. In that instant, the music stopped. The sound waves froze in place, their final ripple imprinting a specific, preferred scale onto the distribution of matter. Think of it like a stamp pressed into the cosmic dough just before it finished baking. That stamp left a subtle, spherical shell of slightly higher density, a fossilized sound wave with a radius of about 500 million light-years. This is the cosmic ruler. As the universe expanded, this preferred scale was stretched along with it. Today, by mapping the precise positions of millions of galaxies in enormous sky surveys, astronomers can find this imprint. They look for a subtle statistical preference for pairs of galaxies to be separated by this specific, stretched distance. It is not that we see a single shell, but that the overall distribution of galaxies in space carries this ghostly rhythm, a faint echo of that ancient cosmic sound. The true power of this ruler is that we know its original size with incredible precision from our understanding of the early universe. By measuring how large this scale appears to be at different distances, and therefore at different epochs in cosmic history, we can directly track how much the universe has stretched over billions of years. The results are unequivocal. When we look back in time, the Baryon measurements show us a universe that was expanding more slowly. The ruler was smaller in the past. When we measure it in the more recent universe, it is larger, confirming that the expansion rate has increased. The cosmic stretch has been accelerating. This is not a measurement based on the tricky brightness of a dying star. It is a geometric test, a direct readout of the universe's expansion history, written into the large-scale structure of everything we see. The fact that this completely independent method, born from the frozen sound waves of creation, confirms the same accelerating reality as the supernova and the cosmic microwave background, leaves no room for doubt. The paradox is real. The universe is not just expanding, it is being pushed apart by a force that defies our deepest understanding of physics, and the evidence is now etched into the very skeleton of the cosmos. These discoveries leave us standing at the edge of a profound philosophical abyss. We have mapped the stars and traced the history of the cosmos back to its first moments, only to find that the universe we thought we knew is a mere shimmer on the surface of a vast, dark ocean. 95% of everything that exists is made of substances we cannot see, cannot touch, and cannot even detect directly. Dark matter and dark energy are not just hidden, they are fundamentally other, operating outside the known rules of our physical reality. This forces upon us a state of cosmic humility, a sobering recognition that our perception of the universe is not just limited but potentially illusory. We are like beings who have only ever seen shadows, trying to describe the objects casting them with no concept of light or form. Our entire scientific enterprise, built on observation and experiment, is currently powerless to interact with the dominant components of existence. This is not a temporary gap in our knowledge, it is a fundamental boundary to our senses. The accelerating universe challenges one of the most cherished principles in science, the Copernican principle, which asserts that we do not occupy a privileged or special place in the cosmos. Yet, we find ourselves in a strangely special moment, a fleeting cosmic window where the density of matter and dark energy are comparable, allowing for the formation of galaxies, stars, and planets capable of hosting life. If dark energy had been slightly stronger, the universe would have been ripped apart before life could form. If it had been weaker, the cosmos would have collapsed long ago. This apparent fine-tuning is staggering. Are we the beneficiaries of a cosmic accident, a random roll of the dice in a multiverse of dead universes? Or does our ability to observe the cosmos somehow depend on its specific, life-permitting properties? This pushes our inquiry from the solid ground of physics into the misty realms of metaphysics. We are left to wonder if the universe is ultimately comprehensible to the human mind. Perhaps we are not decoding the master blueprint of reality, but merely learning to read the labels on a few visible boxes in an infinite, darkened warehouse. The greatest mystery may not be dark energy itself, but what its existence reveals about the ultimate limits of our own understanding. The next great leap in this cosmic investigation is already underway, not with a single telescope, but with a coordinated assault of next-generation observatories. These are not mere upgrades, they are entirely new eyes on the sky, designed from the ground up to probe the dark universe. The European Space Agency's Euclid satellite, NAS, a forthcoming Nancy Grace Roman Space Telescope, and the ground-based Vera C. Rubin Observatory in Chile represent a new era of precision cosmology. Their mission is to create the most detailed three-dimensional map of the cosmos ever produced, charting the positions, shapes, and distances of billions of galaxies across immense stretches of space and time. This monumental cartography project is fundamentally a hunt for the invisible. By studying the subtle, systematic warping of galaxy shapes, a phenomenon known as weak gravitational lensing, these instruments will trace the distribution of dark matter, revealing its hidden scaffolding in stunning detail. But their primary target is the history of expansion itself. They will track how the cosmic stretch has changed over billions of years with a precision we can only dream of today. This is the core of the investigation, to measure the equation of state of dark energy. Is its repulsive pressure perfectly constant, unwavering over time, as a simple cosmological constant would suggest, or does it fluctuate, strengthen, or weaken, pointing toward a dynamic field like quintessence? The difference in the data would be subtle, a tiny deviation in the way the expansion rate has changed, but it would be everything. It would tell us if dark energy is a fixed feature of empty space or an active, evolving component of the cosmos. These missions are, in essence, gigantic dark energy experiments. The torrent of data they will produce over the coming decade could finally provide the crucial clue, the single piece of evidence that tips the scales in this grand theoretical debate. The answers we seek are written in the large-scale structure of the universe, and we are now building the tools to read that story with perfect clarity. This line of reasoning is known as the Anthropic principle, and it stands as one of the most controversial ideas in all of modern science. It offers a deceptively simple answer to the puzzle of fine-tuning. The fundamental constants of nature, like the incredibly small value of the cosmological constant, might have the values they do for one straightforward reason. If they were any different, we would not be here to notice. A universe with a slightly stronger dark energy would have blown itself apart before the first star could form. A universe with slightly weaker dark energy might have collapsed back on itself in a big crunch eons ago. The fact that we observe a universe so perfectly balanced for life, according to this principle, is not a miracle. It is a selection effect. We are inevitable observers of a cosmos that permits observation. This idea finds a powerful, if speculative, home within the concept of the multiverse. If our cosmos is just one bubble in a vast, frothing foam of universes, each with its own unique, random set of physical laws and constants, then the mystery vanishes. In an infinite landscape of dead, sterile universes, it is no surprise that conscious beings arise only in those rare, golden pockets where the numbers just happen to be right. The vacuum energy is not fine-tuned. We are simply the lucky winners of a cosmic lottery. For some, this is a profound and elegant solution. For others, it is a philosophical retreat, a surrender in the quest for a deeper, physical explanation. Critics argue that the Anthropic principle is fundamentally non-predictive. It does not tell us why the constants have their specific values, only that they must be compatible with our existence. It replaces a puzzle of physics with a tautology of logic. This debate forces us to confront a deeply unsettling question about the nature of science itself. Are some properties of the universe simply brute facts, random outcomes that require no further explanation beyond the fact that we are here to record them? Or is this line of thinking a dead end, a way of giving up on the dream of a complete and fundamental theory of everything? The answer we choose will ultimately shape not just our model of the cosmos, but our very understanding of what it means to seek an explanation at all. This pattern of acceleration may not be unique to our current era. To find its echo, we must journey back to the very beginning of everything, to a fleeting moment of unimaginable violence known as cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe is thought to have undergone a growth spurt of epic proportions, expanding faster than the speed of light itself. This was not an explosion into space, but a staggering stretching of space-time. The driving force behind this primordial acceleration was not dark energy, but a hypothetical energy field physicists call the inflaton. This field is thought to have temporarily endowed the vacuum of space with a powerful negative pressure, creating a repulsive form of gravity that blew the universe up from a subatomic speck to a vast cosmic domain in less than a blink of an eye. This inflationary surge solved several profound puzzles in one elegant stroke. It ironed out the universe, making it geometrically flat. It smoothed away any major irregularities, creating the remarkably uniform canvas we see in the cosmic microwave background. And then, just as suddenly as it began, inflation ended. The inflaton field decayed, dumping its immense energy into the creation of the hot soup of particles and radiation that would eventually form stars and galaxies. The universe settled into the long, decelerating expansion governed by gravity, a phase that would last for billions of years. The modern acceleration we see today presents a hauntingly familiar story. Once again, the cosmos is in a phase of speeding up, driven by a form of energy with repulsive gravity. This raises a deeply compelling question. Is dark energy a faint remnant of that initial inflationary field, a ghost from the dawn of time that has reawakened? Could the universe have a natural tendency, a built-in predisposition, for these dramatic bouts of accelerated expansion? The energy scales are vastly different, of course. The push of inflation was unimaginably stronger than the gentle nudge of dark energy, but the conceptual parallel is too striking to ignore. It suggests a profound symmetry, a rhythm to cosmic history where acceleration bookends the story of the universe. Uncovering a link between these two epochs would be a monumental step toward a unified theory, one that seamlessly connects the physics of the very large with the laws that govern the very first moment of existence. This single number, W, holds the power to classify the unknown. It is the equation of state parameter, a deceptively simple symbol that quantifies the essence of dark energy itself. Think of it as a cosmic identification card, a single value that defines the relationship between the pressure and energy density of this mysterious force. For the simplest model, Einstein's cosmological constant, this value is locked in at exactly -1. This specific number represents a perfect, unwavering balance, an energy woven into the vacuum of space that never strengthens or fades. A universe with a W of -1 expands in a very particular way, leading to the long, cold fade of a heat death. But what if this number is not -1? Our current best measurements show W is incredibly close to that value, but the margin of error, while small, opens a door to breathtaking possibilities. If future observations were to find that W is consistently different from -1, even by a tiny amount, it would instantly shatter the simple cosmological constant model. Such a discovery would be the definitive proof that dark energy is not a static property of empty space, but something dynamic and evolving, a field like Quintessence that changes over cosmic time. The universe's acceleration would then be a chapter in an ongoing story, not a final sentence. This quest for precision is what drives our most powerful new telescopes. They are not just taking pictures of the cosmos, they are conducting a forensic audit of expansion history, measuring the subtle changes in the growth of cosmic structure across billions of years to pin down this number with unerring accuracy. The implications become even more profound if W is found to be less than -1. This hypothetical realm is known as phantom energy. The name is fitting, for its properties are truly ghostly and bizarre. Phantom energy would possess a negative pressure even stronger than that of the cosmological constant. In such a scenario, the repulsive force would not merely remain constant, it would actually grow more powerful as the universe expands. This would set the stage for the most dramatic finale imaginable, the Big Rip. The acceleration would not just continue, it would run away with itself, growing exponentially until every structure in the cosmos, from galaxy clusters to the atoms in your body, is torn apart by the stretching of spacetime itself. The precise value of W is therefore much more than a technical detail for cosmologists. It is the key that unlocks the ultimate fate of everything. Is our universe destined for a quiet, frozen end, or a violent, explosive demise? The answer is written in this one elusive number. Even the faintest whisper of the Big Bang carries a hidden message about dark energy. This whisper is known as the integrated Sachs-Wolfe effect, a subtle shift in the temperature of the cosmic microwave background. To understand this, picture a photon, a particle of light, from that ancient afterglow traveling for billions of years to reach our telescopes. On its long journey, it must pass through the vast gravitational hills and valleys created by superclusters of galaxies and the immense voids between them. When a photon rolls down a gravitational hill into a deep cluster, it gains energy, making it appear slightly hotter. When it must climb out of that valley, it loses energy, appearing slightly cooler. In a universe dominated by matter and slowing down, these gains and losses would perfectly balance each other out. The photon would arrive at our detectors with its original energy nearly unchanged. But our universe is not playing by those rules, because dark energy is causing an accelerated expansion. The very fabric of spacetime is stretching faster than the gravitational structures within it. The immense gravitational hills and valleys are not static. They are actually decaying, flattening out as the photon passes through them. It is like a traveler crossing a mountain range that is sinking into the plains as they walk. The photon climbing out of a decaying gravitational well loses less energy than it gained falling in. This imbalance leaves a specific, net positive imprint on the photon, a tiny warming of the cosmic microwave background in the directions of these large-scale structures. This signal is incredibly faint, but by meticulously comparing maps of the CMB with maps of the distribution of galaxies and dark matter, astronomers have successfully detected this very imprint. It is a subtle confirmation, a cosmic echo that whispers, yes, the universe is indeed stretching in a way that can only be explained by a pervasive, repulsive force acting against gravity itself. Perhaps the cosmic acceleration is not a force but a phantom, a trick of perspective on the grandest scale imaginable. This idea challenges the very foundation of our measurements, suggesting that our place within the cosmic web might be painting a distorted picture of the whole. For centuries, cosmology has relied on the Copernican principle, the assumption that our location in the universe is not special or unique. We assume that what we see from our galactic neighborhood is a fair sample of the cosmos as a whole. But what if that assumption is wrong? Some cosmologists propose a radical alternative known as the backreaction hypothesis. It suggests that the colossal structures of the universe, the immense filaments of galaxies, and the correspondingly vast, empty voids between them are not just passive features. Their gravitational influence might actually be feeding back into the overall expansion rate, warping our global measurements. Think of the universe not as a uniform loaf of raisin bread, but as a block of Swiss cheese with dense, heavy regions and enormous, empty bubbles. If our Milky Way galaxy happened to be situated inside one of these exceptionally large cosmic voids, our local gravitational environment would be unusually weak. With less matter around us to pull things together, the space within our void would expand faster than the cosmic average. From our privileged vantage point deep inside this bubble, when we look out and measure the recession of distant galaxies, we might misinterpret this local fast expansion as a global phenomenon. The entire universe would seem to be accelerating when in reality, we are simply residing in a unique and underdense part of the cosmos. It is a compelling and elegant idea, one that attempts to solve the dark energy puzzle by replacing it with a cosmic mapping error. However, when scientists run the numbers and create sophisticated computer simulations of this Swiss cheese universe, the effect consistently falls short. The calculated back reaction from even the largest observed voids is simply too small, by a significant margin, to produce the powerful, smooth acceleration we measure. It cannot account for the data from supernova, the cosmic microwave background, and Baryon acoustic oscillations all at once. While it may not be the ultimate answer, the back reaction hypothesis serves as a crucial philosophical check. It forces us to remember that our data is always collected from a single point in this vast and lumpy cosmos, and that the map we draw of the whole universe is inevitably filtered through the lens of our own local neighborhood. Our quest for a final answer must always account for the possibility that we are not just observers of the cosmos, but participants within its intricate and uneven structure. The final answer may lie in a theory that does not yet exist. For over a century, physics has been split into two magnificent but incompatible kingdoms. General relativity masterfully governs the cosmic realm of planets, stars, and the expanding universe, while quantum mechanics rules the bizarre and probabilistic world of the atom. Each is brilliantly successful in its own domain, but they speak different languages and obey different rules. The dark energy paradox, the inexplicable feebleness of the vacuum energy, is a direct clash between these two kingdoms. It is a screaming signal that we are missing the unified law that connects the very large with the very small. This is the quest for quantum gravity, the holy grail of modern physics, and it may be the only path to resolving the accelerating universe. The solution demands a framework where spacetime itself is not a smooth, continuous stage, as Einstein described, but has a discrete quantum structure at the tiniest possible scale. We are searching for the atoms of space and time. Leading this charge are ambitious candidate theories like string theory and loop quantum gravity. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrational modes of these strings give rise to every particle and force in nature, weaving gravity and quantum mechanics into a single tapestry. One of its most profound and controversial implications is the concept of the landscape. This is a vast, theoretical collection of possible universes, each with its own unique laws of physics and, crucially, its own value for the cosmological constant. In this unimaginably huge cosmic garden, our universe is just one flower with a specific, randomly selected vacuum energy. The value we measure is not fine-tuned by deeper law, but is simply a prerequisite for our existence. We find ourselves in a universe that allows for galaxies and life because we could not arise anywhere else. While this anthropic reasoning offers a potential escape from the fine-tuning puzzle, it leaves many physicists longing for a more deterministic, testable explanation. The great challenge for all these theories of quantum gravity is the staggering energy scale required to probe the fabric of spacetime directly. Testing their predictions would require a particle accelerator larger than our entire solar system, pushing them far beyond the reach of any foreseeable experiment. For now, they remain magnificent mathematical edifices awaiting a connection to observable reality. So the accelerating universe is more than a puzzle, it is a cosmic beacon. Its paradoxical light is guiding us toward the next great revolution, an upheaval in our understanding that will force us to redefine nothing less than space, time, and the meaning of a vacuum. The mystery of dark energy is not a wall but a doorway. This profound mystery has leapt from the pages of scientific journals and into the very fabric of our culture. You can find its echoes in best-selling books and blockbuster documentaries, where the enigmatic force of dark energy is presented as the ultimate cosmic villain or the key to humanity's final destiny. It has become a powerful symbol in our collective imagination, a real-world puzzle that rivals the most creative science fiction. This is not merely a topic for specialists in observatories. It is a story that speaks to a fundamental human urge, the deep-seated need to explore the unknown and find our place within it. The accelerating universe reminds us that reality itself is far more bizarre and magnificent than our everyday lives suggest. It challenges the comfortable assumption that we have unraveled the basic rules of existence, presenting us with a genuine frontier that demands new tools and new ways of thinking. For a young person first learning of this cosmic defiance, it is not just a fact to be memorized, it is an invitation. It sparks a fire of curiosity that inspires the next generation of astronomers, physicists, and philosophers to pick up the torch. They are the ones who will question the doctrines we currently hold sacred, who will dare to propose the seemingly impossible, and who may one day decipher the true nature of the dark cosmos. The story of the expanding universe paradox is at its heart a human story. It reflects our timeless wonder about our own origins and our ultimate fate, set against the breathtaking backdrop of a universe that is actively and mysteriously writing its own final chapter. Yet even a discovery as monumental as cosmic acceleration must face the gauntlet of scientific scrutiny. Not every researcher is convinced that dark energy is the only answer. A small but vocal group of scientists points to potential cracks in the data itself, suggesting that the entire paradigm could rest on a misinterpretation. What if the distant supernova appear fainter not because they are farther away in an accelerating universe, but because their light is being subtly dimmed on its long journey to Earth? Interstellar dust drifting between galaxies could potentially absorb and redden starlight, creating a false signal of acceleration. The teams who made the original discovery have painstakingly modeled and corrected for this dust, but critics argue that the properties of cosmic dust over billions of years are not fully known. Could an unusual type of dust, or more of it than we think, be fooling us? Another possibility is that the supernova themselves are not perfect standard candles. What if these stellar explosions were intrinsically fainter in the early universe? If the composition of stars changed over cosmic time, the explosions they produce might have been different, less bright, in the distant past. This cosmic evolution of the supernova could mimic the effects of acceleration without any mysterious dark energy at all. Then there is the more radical tired light hypothesis. This idea proposes that light simply grows tired over immense distances, gradually losing energy and shifting to the red without any expansion of space at all. In this static universe, a photon might interact with the quantum foam of spacetime or some other unknown field, slowly reddening as it travels. While this elegantly explains the redshift, it creates far more problems than it solves. It cannot account for the time dilation seen in the light curves of distant supernova, nor can it explain the precise patterns in the cosmic microwave background, or the observed abundance of light elements from the Big Bang. The evidence for an expanding, evolving universe is woven into too many independent threads for tired light to unravel. These alternative interpretations remain on the fringe of cosmology, their explanations often creating more mysteries than they resolve. But their value is undeniable. They act as the essential devil's advocate, pushing mainstream science to cross-check every assumption, to refine its models, and to seek even more robust evidence. This constant, rigorous debate is not a weakness of the scientific process. It is its greatest strength, ensuring that our picture of the cosmos, however strange, is built upon a foundation that has been tested against every conceivable challenge. When we step back from any single telescope or dataset, the true power of the evidence comes into focus. Each line of inquiry, from the fading light of supernova to the frozen ripples of Baryon acoustic oscillations, tells a small part of the same grand story. The cosmic microwave background gives us a blueprint of the infant universe, while the integrated Sachs-Wolfe effect reveals the subtle decay of its gravitational landscape over billions of years. Each of these methods stands on its own, a separate path through the cosmos with its own unique assumptions and potential pitfalls. But the extraordinary thing is not their independence, it is their convergence. They all arrive at the same startling conclusion, pointing to a single moment in cosmic history, roughly 5 billion years ago, when the universe itself shifted gears. This is not a conclusion built on one fragile pillar. It is a cathedral of evidence where every arch and buttress supports the same incredible narrative of an accelerating cosmos. The paradox of this acceleration is therefore not a fluke or an artifact of our measurements. It is a signal that has been imprinted into the very fabric of multiple, independent observational realities. This profound coherence gives physicists a deep and abiding confidence. We may not yet understand what dark energy is, but we are now virtually certain that the phenomenon it describes is undeniably real. The mystery has therefore deepened, transforming from a question of whether the acceleration is happening to the far more challenging question of why. This solidifies the expanding universe paradox not as a curious anomaly, but as the central puzzle of our time, a challenge that defines the frontier of 21st century physics. So where does this leave us standing before the vast unknown? The expanding universe paradox remains one of the greatest unsolved mysteries in all of science, a humbling testament to the limits of our current knowledge. We have mapped the acceleration with stunning precision, yet we are no closer to understanding its fundamental nature. Is dark energy truly Einstein's simple cosmological constant, a fixed feature of the vacuum? Or is it a dynamic field like Quintessence, slowly evolving and changing the rules over cosmic time? Could it be that we are witnessing not a new force, but the first crack in Einstein's theory of gravity, a sign that general relativity must be rewritten on the largest scales? The possibilities stretch even further into realms of physics we have not yet even conceived. The stubborn Hubble tension, that disagreement between the local and ancient expansion rates, is not just a minor statistical fluke. It is a persistent ache, a potential signal that our standard model of cosmology is missing a crucial ingredient. And the cosmic coincidence problem, the eerie timing that places us at the brief moment when matter and dark energy densities are comparable, continues to whisper that either our universe is bizarrely fine-tuned or our understanding of its history is deeply flawed. These are not minor gaps, they are chasms. Bridging them will demand more than just bigger telescopes. It will require a flood of new data from observatories like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, data that will scrutinize the expansion history with unforgiving precision. More than that, it may demand a theoretical breakthrough, a paradigm shift as profound as those sparked by relativity and quantum mechanics a century ago. The journey to solve this paradox is far from over. It is an active, thrilling adventure, one that calls for a blend of profound humility and boundless creativity. The cosmos is presenting us with a riddle that challenges the very foundations of physics, and the solution will undoubtedly rewrite our story of the universe. Our exploration of this cosmic paradox leaves us with a universe that is both magnificent and deeply mysterious. We have moved from the steady expansion Hubble first witnessed to the astonishing discovery of acceleration, a phenomenon that defies the very pull of gravity we thought was universal. This journey through the enigma of dark energy reveals a cosmos where the dominant forces are not just invisible, but utterly alien to our current physics, challenging the foundations of both general relativity and quantum theory. This is far more than a technical puzzle for specialists. It is a fundamental inquiry into the fabric of reality itself, forcing us to confront questions about the ultimate fate of all things and the very limits of what we can know. Let this understanding fill you with a renewed sense of wonder when you gaze at the night sky. Let it inspire you to keep questioning, to keep exploring, and to remain curious. The history of science teaches us that the greatest revelations are often found waiting just beyond the edge of our current comprehension. What do you think lies at the heart of this cosmic acceleration? Share your thoughts and join this ongoing quest to unravel the deepest secrets of our expanding universe.